lines of fill in some number provided by the facilitator. That number is going to be 50, just 50. And my name is Megan. If you guys at any point, like normally I try to look up and be like, do you guys have any questions or like that kind of stuff. But if at any point, like I don't see you or if I'm looking down and you do have a question, you can either like say, hey, can you like go back or like don't be afraid to be like, stop. Quick like overview, kind of what's going to go on. I have 8 multi-part questions, so it's very similar to the other reviews that I've had throughout the semester. If you've looked at the review, this is obviously a cumulative exam, so some of these questions are from like, actually, some of them are from like my old reviews just because, you know, I was trying to basically build a review that had the most amount of material covered, and so I went through and pulled out things that covered multiple concepts. So you might see some similar problems if you've been to one of my review sessions before. Are there any questions? Okay, so one more time, there are surveys at the front table at the like middle, I guess, right there. If you could fill one out, as long as it's done by the time the session is over, that's fine. But if you want to leave it where you're at, that's fine. If you want to bring it up to me, just please don't walk in front of the projector. And with that, I'm going to go ahead and get started. If you want to follow along and you don't have a hard copy of this, you can go to the website. It's, well, you can Google. I'm just going to put Google because it's a little bit easier. UCF Study Union WordPress. And it should be the first thing that comes up. You're going to go to the top bar. It'll have like biomolecular sciences, biology, chemistry, and then physics. Go to physics with Megan, and then there will be a formula sheet and a review there. Any other questions? Cool, okay. I'm gonna go ahead and start then. Again, just UCF Study Union WordPress, so. So we actually start out with 2D kinematics. I've said this to a few people I know. I felt like it would be a better idea to start with 2D than 1D because 2D kind of builds on 1D. So like, I feel like if you understand this, you should be able to understand the easier stuff. But okay, so the first question is that we have a football and it's kicked with an initial velocity of 30 meters per second at an angle of 30 degrees with the horizontal. You need to find the initial horizontal velocity, velocity at peak height, the time of flight, the range, and the peak height of the football. So we're going to go ahead and write down the information that we have, which is that we have a VI, so that's velocity initial of, that's a little small, I'll write bigger, 30 meters per second. We also have an angle of 30 degrees with the horizontal, and then we need to find the initial horizontal velocity, which would be VI what? Which variable would we consider? Good, all right. VIX, we need velocity at the peak height. So we'll just put initial velocity at peak height. So this would be horizontal velocity, my bad. So horizontal velocity at the peak height, so VIX at peak. So the time of flight, so we'll just put that as t, lowercase t. The range, which is r, and the peak height of the football, so we'll have h. Okay? Any questions about the current setup? All right, so we're going to go ahead and draw a picture because drawing pictures in physics makes life a lot easier. So we're just going to have, right here, we kick the football, it's going to hit some peak, and it's going to come back down and hit the ground, right? So we said that we kicked the football and it was traveling at a velocity of 30 meters per second. So I'm going to write that here. And at an angle of 30 degrees with the horizontal. All right, so first bit of strategy, I guess. So the first part is just to find the horizontal velocity. So that should be pretty straightforward. So find VIX. We are going to use the information from this first part to find the initial velocity at, or not the initial, sorry, the velocity at the peak height. So peak height V. So we can use the information from this to find this. And then we're going to find time to here. So actually, I'm going to go ahead and just start going piece by piece, and that way it's a little more cohesive. All right, so the first part is to find VIX. How do you guys want to set up that problem? What do you think we need to use here? 30 times cosine. Okay, so if we were to draw a triangle here, we would have that this is the adjacent, this is the opposite. And what are we trying to find again? VIX. So would it be the adjacent, the opposite, or the hypotenuse value? Sorry if there are a lot of voices. Adjacent, good. So what would we use? Good, yeah. 30 meters per second times cosine of 30 is going to be equal to VIX. So if you guys want to pull out your calculators, we should have 30 times cosine 30. Cosine 30. What'd you guys get? Yeah, so should be, VIX should be 25.98 meters per second. Generally, she gives 4 significant figs, so I'm going to go with that. All right, so the second part was to find the initial horizontal, second part was to find the horizontal velocity at the peak height. So what does that mean exactly? We just found the horizontal velocity at basically the initial point, and then now we're trying to find it at the peak. How would we go about doing that? Would it be 0? What do you guys think? Okay, can you explain why?
It's the same in the horizontal. It doesn't matter.
Good. So, sorry, I have to repeat myself in case people are listening online. But what he just said is that the horizontal velocity will remain the same at the peak. And the reasoning there is that we're assuming that there's no air resistance, which should be added up here. So assume no air resistance. Sorry, I forgot to add that in. You're assuming no air resistance, so you don't really have any forces acting on the horizontal velocity. So it's just going to keep going at 25.98 meters per second in the horizontal. Because remember, we're going this way, right? Does everybody understand where that comes from? Any questions? All right. So horizontal velocity will remain the same at the peak as it is at the beginning, so it will still be 25.98 meters per second. All right, so then the next part asked you to go ahead and find the time. So how do you think that we need to go about finding the time?
Acceleration equals velocity over time.
Okay, so that's a way of doing that. Do we have all of the things that we need there?
You can find velocity by doing 30 sine 30.
Okay, good. So sorry, can you repeat what formula you said?
30 sine 30 to get the vertical velocity.
Okay, so we'll go ahead and find that first. So we'll have V by Y is going to be equal to 30 sine 30 degrees. Remember, this is meters per second. So what would you guys get for VIY? $15. Did everybody get 15 meters per second? Good. So VIY would be 15 meters per second. So we're looking for time still. So we have to use a kinematic equation. So I'm going to go ahead and stick this up just so that you guys can see them. Which kinematic equation do you guys want to use? Yeah.
When we did this last time,
Mm-hmm.
you didn't use a kinematic equation. You just used acceleration equals velocity over time.
Okay.
And then you had time equal velocity over 10 because it's gravity. Multiplied by 2.
Okay, so there are more than one way. I guess there's more than one way to solve it, but I guess guess we could go that way if you guys would prefer to go that way. All right, so it's kind of up to whatever you guys want to use. So the first way to solve this is, I'm trying to think, I think it's this one here. So remember, we're in the vertical direction now, trying to find the time that it would take to get to the, or the time of the entire flight. So let's go ahead and do, okay. We're going to go ahead and use the kinematic equation that I just circled. So that's VF is equal to VI minus GT. So if you guys remember your kinematic equations in the other direction, G is normally acceleration, but since we're in the vertical direction, we're using gravity. So that's where that comes from. But we have a VF of what? What is going to be 0? Why is it 0? So we're actually, in this first part, we're trying to find the time that it takes for half of travel, basically. So we're going from here to here. So why would the velocity be 0 here, the vertical velocity? Good. So when you throw something in the air, kick something, and it's got a vertical direction, it's going to hit a 0, and then it's going to start coming back down, right? So the velocity is going to start here, travel, 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 and while it's traveling upwards, what is acting downwards? What acceleration? Gravity. So gravity is going to be pulling it downwards, and it's going to hit that midpoint. It's going to be 0, and then gravity is going to take over and start pulling it back down to the ground. So we have a V final here of 0 meters per second. We just calculated our V initial. It's going to be 15 meters per second. Then we have minus 10 meters per second squared. You can also use 9.8. Generally, she has you guys use 10, so we're just going to use that here. And then that is going to be time, or multiplied by t. So you can rewrite this equation to solve for t. It would be, oh my gosh, I can math. All right, so 15 meters per second over 10 meters per second squared equals t. I think I did that right. Minus. Yeah, that looks right. Okay, so what do you get for your time? 1.5. Right, so 1.5 seconds. So remember, we said that this was half of the distance, right? So what do you need to do to get the whole distance? Times 2. So time should only be 3.0 seconds. That would be the actual, so this is half. Sorry, my handwriting is getting weird because I have wires here. And this is the full time, right? Okay, any questions about what I just did there? Okay. All right, so then what is the next part that we asked for? So time of flight, then we need the range. So there are actually 2 ways of solving for range. There's one based off of a formula, which is right here. So if you have your formula sheet, it's this formula. Or you can do it a little bit differently, whatever you're most comfortable with. Okay. So I'm going to start with the formula just because she generally gives the formula. So part 4, we're looking for range, is going to be equal to VI squared sine 2 theta divided by gravity. Okay, so that's given on the formula sheet. At all? Oh yeah. Better? Good. Okay, thank you. Yeah, I can't see the live stream, so if there's an issue, just let me know. Is there an issue?
Yeah.
What? We're good? Okay, cool. Thank you. All right. So anyway, so we have the range formula. So that's the VI squared sine 2 theta over gravity. So you pretty much have all these numbers already, so you're just going to plug them in. Right? So range is equal to 30 meters per second squared sine, I don't like this here. Okay, 2 times 30 degrees over 10.0 meters per second squared. So when you, just FYI, when you plug this in, you're actually doing 2 times 30 and then sine of that, okay? So you should get r equals 79.5 meters. Did everybody get that?
What did you say?
79.5 right here, sorry. All right, so there's a second way to do it, and you guys are probably going to be like, that's so much easier, why didn't you tell me that first? But, you know. Okay, so the second way to do it is just to take the VIX, because you're across a, what surface? Horizontal surface. So you do VIX times the time that it took to travel, which would be, actually, sorry, I just realized that when I did this, I did 9.8 meters per second squared, so you might have a slightly different number. What is it?
77.9.
Okay, sorry. So 77.9. Yeah, no, I normally do 9.8 meters per second squared, but sometimes I might have a little bit different numbers. Just let me know if I screwed up somewhere. So the other way to do it is VIX times the time that it took basically to travel. So that would be the 3.0 seconds, would also be equal to your range. So VIX was the 25.98 meters per second times 3.0. You should get the same answer. Let me double check that though. Yeah, so 77. So this would still give you range equals 77.9 meters. Cool. Two ways to do it, whichever you feel most comfortable with. She should give you the range formula, so if you just want to go off of that, that's totally fine. If you're more comfortable doing that way, then that's fine too. All right, the last part is the peak height of the football. Part 5. Okay, so the last part is to find the total height. So we already talked about how at the peak height, we're still going to have a velocity in the y direction of what? You guys remember? So Vy at peak height, 0. Good. So 0 meters per second. So if we look at our kinematic equations real fast, we're trying to find height. So do you guys see a quantity here that represents height in your 2D kinematic equations, your vertical kinematic equations? This one? Yeah, good. So when you consider, refers to like the position, right? So the initial position would be what? How many meters? 0. So this is going to be your peak height at when you have a final position at the peak. So this would also be equal to height, just heads up. So we can go ahead and use this formula then. So we have, this is our final position, or final velocity is going to be 0 meters per second. Our initial velocity is what? 15 meters per second. What else do we have? So the other things in there are g equals gravity, so 10 meters per second squared, and we can just plug it in. So we would have 0 meters per second squared equals the 15 meters. Sorry, I'm running out of space. I might get another piece of paper. That'll work. I'm going to continue number 5 down below. All right, so I'm going to rewrite it here. So the formula that we're using is the Vf squared equals Vi squared minus 2g times height, right? So that's the fourth one underneath vertical displacement. So we know that our y direction final velocity is going to be 0 meters per second squared equals Vi squared, which we said was the 15 meters per second squared minus 2 times 10 meters per second squared times height, right? So then you can just rearrange this and solve for height. So you'll get negative 15 meters per second squared is going to be equal to negative 2 times 10 times height. We have negatives on both sides, so you can just make it a positive by dividing or multiplying by 1. So this squared is equal to 220h, and this will be 225 meters per second. Meters squared per second squared is equal to 20 meters per second squared times height. So you just divide it and solve for height. What'd you guys get? 11.25. Sounds good. Meters. Sorry, I cut off the M. All right. Any questions? We're good? All right, nobody's saying anything, so I'm assuming we're all good. So it should be 11.25, and that's basically the distance in our picture from here to here. Right, okay. All right, I'm gonna go ahead and go to number 2 if nobody has any questions. If at the end you wanna snag a picture of anything, or if you need me to stop or slow down, just let me know. All right, so the next question is forces. So moving on from 2D kinematics. So we have a crate of mass 100 kilograms is being pulled up an inclined plane with an applied force of 1100 newtons. The plane is inclined at an angle of 37 degrees. The coefficient of friction, mu, between the crate and the incline is 0.3. Determine the weight of the crate, the normal force acting on the crate, the frictional force acting on the crate, the net force acting along the incline, and the acceleration of the crate on the incline. So a couple different parts. So we're going to write down what we know. We have a mass of 100 kilograms. We have an angle equal to 37 degrees. We have a coefficient of friction mu equal to 0.3. And we have an applied force equal to 1100 newtons. Okay. All right. So the question asks for the weight, the normal force, so force, normal, the normal force, the frictional force, the net force, and the acceleration, so A on the incline, right? So let's go ahead and start. I'm going to kind of skip the known unknown strategy. I'm going to try and use up as much paper since I kind of ran out of room on the last one. But we have our knowns, we have our unknowns, so we'll go ahead and start. First one, how do we go about finding weight? Yeah, so actually, I should probably draw the free body diagram first. Yeah, so with any forces question, always draw a free body diagram. Do not do what I just almost did. So this is really terrible incline. This is not drawn to scale at all. We're gonna pretend that this is a right angle. And this is our 37 degrees. And then we have a box sitting on it, right? And it is being pulled up the incline, right? So if we were to draw our arrows on here, we would have an applied force going in this direction. This is our applied. We have a force of friction acting this way. We have, you know what, I kind of hate this picture. I'm gonna draw it a little bit bigger so you guys can see. Would that be better? Okay, sorry. I realize this is a very small screen. That'll work. All right, so I'm gonna redraw our free body diagram, much larger. So we have a box. It's being pulled up. Here we have a right angle. This is our force applied. So FAPP. We're gonna have a force of friction acting downwards. We're going to have our weight. And then we're going to have the normal force by the surface, right? So when we draw a little triangle right here, we'll get a right angle right there. And this is our 37 degree angle, and this would also then be 37 degrees. So, sorry. So basically this is 37, this is our force normal. Everybody see that? Okay. All right, so now we have a decent picture. So let's go ahead and do the weight. So you guys said that the weight is equal to mass times gravity. which is correct. So weight is equal to our mass, which was 100 kilograms, times the gravity, which she uses the 10 meters per second squared, but I normally use 9.8 meters per second squared, so I'm going to go ahead and use that. And we're going to get that weight is going to be equal to 980 newtons. Okay? So that's the easy part. So the next part is then asking for the force normal. So when we look at our picture here, how do you guys want to try going about finding the normal force? So we have to use the angle and use trig to find it, right? Yeah, good. So this downward part is going to be the adjacent. This will be the opposite, right? So we're going to use what value do you guys think? Cosine. Good. Yeah. So we use cosine. So we're going to come up here again. So force normal is going to be equal to what? What times cosine? Good. So either force of gravity or weight. So we can write weight. Sorry, I can't talk. We're going to write weight, and then we're going to do cosine of the angle. You guys remember that? Okay. So force normal is equal to weight times cosine of theta. So F normal, if you're going to plug in the numbers, we would have 980 newtons times cosine 37. What did you guys get? Hmm? 782.7? Okay, cool. So 782.7. All right. So the next part was the force of friction. Anybody get anything different? Just making sure. Okay. All right, so the next part is to go ahead and find the force of friction. Make sure that everybody can see. Force of friction equals what? How would we find the force of friction here? Good, yeah, there is a formula. So it's this one. Yeah, so we can use this formula right here, which is the force of friction is equal to mu times force normal. We already calculated our force normal, so it should be pretty easy to find it, or to calculate this times force normal. So we would have the force of friction is equal to mu, which is 0.3, times the force normal, which is right here. This is our weight, times 782.7 newtons. My bad. All right, so what did you guys get? Good, awesome. So force of friction equals 234.8. Anybody get anything different? Oh, sure. So in this case, you're pulling something up the incline, right? So we just calculated that the force of friction was 234.8 newtons. And the force applied in this situation is the 1100 newtons that you're pulling up. Yeah. All right. So sometimes you do include force of friction in the applied force. If it's like sliding down, then you would include the force of friction in finding the force applied. Okay, so the next part is to find the force, the net force. So how do you guys think that we need to find that? Awesome. So she said like you're going to add up the different components. So we have on our free body diagram, we have a force applied because we're pulling some rope up this little incline. So what sign do you think that the force applied should be? Positive, awesome. So we're gonna have a positive sign here. In this direction, we have the force of friction. What do you guys think that should be? Negative. Do we have any other components that are going to affect the overall force on the incline? Okay, I'm seeing some people shake their heads and some people nod. So for those of you that are nodding, what do you think that we need to include? Sorry? Oh, I thought someone said something. Okay, good. So there is a component of the weight of the box, right? So we have weight is downward. So it, as we kind of like drew in this little picture, we have an X component of the weight and we have a Y component of, or sorry, I think I did that the opposite direction. Yeah, so we have, sorry, we have an X component and we have a Y component. This is the X component, this is the Y component. My brain is like frazzled. Anyway, so we need to include the X component in this direction. So how would we represent the weight here then, if we're looking for this? Awesome, so FG sine theta. That's gonna be the Y component, right? All right, so what sign should that be? Negative, awesome. So we're gonna go ahead and write this out then. So the net force in that direction then is going to be the F applied, force applied, minus the force normal, or not force normal, force of friction. Dang. Force of friction plus the component of weight, which is the FG sine theta. Okay? So you can either write it out this way or you can distribute the negative sign if you like that better. I like to write it like this because I think it makes it look a little bit neater. And then what do we need to do next? We need to solve, right? Okay. So F net is going to be equal to the force applied, which we have is 1100 newtons that was given. And then we're going to subtract the force of friction, which we calculated to be 234.8 newtons, plus Fg sine theta, which is, Fg here is just the force of gravity, so you can plug in weight as well if you like to write it that way better. But it's going to be the 980 newtons times sine theta 37. And then you're going to solve for this value. So I have slightly different numbers. All right, so sine 37, did I do that right? Plus, yeah, and then times 980, you're gonna add that to the 234.8, and then 1100 minus that answer. What did you guys get? I don't know if you can see it. Yeah, 275.421. Is that pretty much what you guys got too? Yeah. 275. I don't know if you can like see it. I don't know. Glare. 275. So F net would be equal to 275.4 newtons. And then the next part is to go ahead and find acceleration. So this is kind of going back to kinematics. Or actually, I mean, no, it's not. F net is going to be equal to mass times acceleration. That's a force property, not kinematics, I'm sorry. So we have 275, well, we're solving for acceleration, so we can just rewrite this as A equals F net over mass. So A equals F net, we calculate to be 275.4 newtons over the mass, which was the 100 kilograms. So you should get an acceleration of about 2.75 meters per second squared. Any questions? No? Cool. All right. I'm gonna go ahead and move on to question number 3. So a 65 kilogram cross-country skier is climbing a 2-degree slope at a constant speed of 2 meters per second and encounters air resistance of 25 newtons. You need to find his power output for work done against the gravitational force and the air resistance. So what average force does he exert backward on the snow to accomplish this? If he continues to exert this force and to experience the same air resistance when he reaches a little area, how long will it take him to reach a velocity of 10 meters per second? So once again, we're going to go ahead and write down our knowns. So we have a mass equal to 65.0 kilograms. We have a slope that is 2.0 degrees. We have a speed, so velocity is equal to 2.00 meters per second. Notice that it says constant speed, which means what? No acceleration. Good, so we're going to write underneath that, no acceleration, because that's constant. All right, so, and then he encounters an air resistance of 25 newtons. So we're going to put force AR, that's an R, is equal to 25.0 newtons. So the first part asks for power output. So we're going to look for power. We need to find average force does he exert backward. So force backwards, I guess, on the snow. We'll just put force, I guess. So power applied, force, and same resistance the whole time. So time it takes him to reach, 10.0 meters per second. So again, I'm going to kind of cross these out just because we're going to use as much space as we can. All right, so the very first thing that I kind of pointed out was that we have a constant speed, which means we have no acceleration. What does that say about kinetic energy? All right, I'm going to write out the formula for kinetic energy. So kinetic energy is equal to 1/2 mv squared, right? So if we have a velocity that's not changing, what does that say about kinetic energy? Is it 0? It's constant. Yeah, so this will also be constant. All right, so when this is constant, what does that say about work, force, like net work, net force, and net power? They're all 0, right? So I'm going to write that out. So work is going to be 0, force net is going to be 0, and power net is also 0, right? So that makes solving for the applied power a lot easier because we know that our net is going to be 0. So we can go ahead and start working some of these things out. So we know that to find power, we have formulas. It's on the second page. Yeah, so second page of formula sheet, you have power is equal to work over time, force times displacement over time, and F times V. If you remember, velocity is equal to d over t. You just kind of plug velocity in for d over t. All right, so power is equal to V times F is the one that we're going to use because we have forces and we have velocity. And then we can also remember that, again, kinetic energy is equal to 1/2 mv squared. So let's go ahead and find our power output. We remember that P net is going to be 0 here because, like we said, kinetic energy is constant, which means that our power is going to be constant. So to find the power net, we need to consider all of the things that are kind of at play here. So we know that we have the power that is applied by what? What's the object, I guess, that we're looking at here? The skier, right? Okay, so we're going to have P net is equal to P applied. And then we're going to have a couple of things acting against that applied power. What are those things based on the problem? You guys good? So one of them is air resistance. And then what's constantly acting on all of us in this room right now? Gravity. So we're going to subtract from the applied power by the skier the power done by the air resistance and the power done by gravity. Okay? All right, so we know that this is 0 again, so we're going to go ahead and plug it in to be 0. PA applied. This is supposed to be minus, I'm sorry. PAR plus PG, which means we can rewrite this. We can get to PA equals PAR plus PG. We just rearranged. And from there we can start breaking down the problem a little bit. So we know that P applied is what we're trying to find. So P applied is going to be equal to the power, which can be written, how else? How else can we write that? If we consider our formula here, we can write it out as velocity times the force, right? So velocity times the force by air resistance. And then we also have plus velocity by gravity, or velocity times force by gravity. Sorry, my bad. All right, so these have common terms. So we're actually going to, did I do that right? Yeah, so we're going to write it as velocity and then times the force of air resistance plus the force of gravity. Okay? Everybody see how we kind of broke that formula down? Yeah, maybe. All right, so do we have force of air resistance? Yes. Do we have force of gravity? Do we have velocity? So can we solve for the applied power? Good. So PAPP is going to be equal to velocity was the 2.0 meters per second times force of air resistance is the 25.0 newtons plus force of gravity, which will just be our weight, which is the 65.0 kilograms times 9.8 meters per second squared. Right? Or you can use 10, whichever you're more comfortable with. So we can do 65 times 10 plus 25, 675 times 2. Actually, wait. You know what? Sorry. Go back for a second. I missed something. We're on an incline. I didn't think about the picture. So this is actually wrong. My bad. Sorry. This is why I keep. So it should be mg sine theta, like earlier with our block on the incline. I apologize. I was moving too quickly and wasn't thinking. All right, so you would have, this is still weight though, so it would be the 65.0 kilograms times the 9.8 meters per second squared, or the 10, depending on which you prefer. And it would be sine times 2, because your angle is only 2 degrees. I apologize, I left the sine 2 off. That should be correct. All right, what'd you guys get? Good. So it should be 95.4-ish, right? Is that what you guys got? Depending on if you use the 10 or the 9.8. What'd you guys get? If you use the 90 or the 9.8 instead of the 10 meters per second squared, it should be like 94.5 watts. And if you use the 10 meters per second squared, then it's a 95.4 watts. So either this is if you use acceleration as 10 meters per second squared. I know you guys are generally used to using the 10, so I try to use that occasionally. All right, so we just found the power. Sorry, did someone have a question? Yeah. Maybe. I can't. Sorry, I didn't realize I could do that. Okay. Sorry about that, guys. All right, so then the next question was to find the force applied. So what average force does he exert backward on the snow to accomplish this? So we're going to use the applied force. So we know that our power equation we just talked about is equal to force or velocity times force. So we can say the power applied is equal to velocity times force applied. And just rewrite the equation and solve, right? So looking for force applied, so it would just be force applied is equal to power applied over velocity. Force applied is equal to the 95.4 watts over 2.0 meters per second. I- So you should get about 47.7 newtons. Is that what you guys got?
Yeah.
Cool. All right. I'm running out of space again. All right, so we're going to go ahead and keep moving along, unless you guys have a question. All right, so part 3 asked you to go ahead and find, he's going to continue exerting this force and to experience the same air resistance when he reaches a level area, and asks how long will it take him to reach a velocity of 10 meters per second. So I'll write out, we're going to find a level surface, and we're going to hit 10 meters per second eventually, and we want to find time. All right, so the things that we found so far are the applied power and the applied force. So how do you guys want to start? What number would you guys prefer using, the applied power or the applied force, if you're trying to eventually get down to time?
Can you still use like the power applied that we found, even though we were finding that when it was on an incline of 2 degrees, or do we have to like solve it without the 2 degrees?
Okay, that's a great point. So, so when we were coming basically like up the incline, you had a force that you were applying the entire way, and so you're carrying that power as well. So when we're starting now on the flat surface, what are we starting with? So we're starting with that force that we were still applying, right? So that's what we're going to use basically to find our velocity and then also the time. So this is a great question. So that means, kind of building on what I just said, we're going to use the force that we just calculated. So we just found the force applied is equal to 47.7 newtons. And we can use that to find the net force that's being applied as we're going across the flat surface, and then take that, plug it into some kinematics, and then find the velocity and the time and all that. So, all right, so force applied is 47.7 newtons. We're going to go ahead and find the force net on the flat surface. So what do we have acting? Actually, wait. So we're going to like basically define the net force here. We're going to have to use F applied and minus force of air resistance. Okay. All right, so that would be the 47.7 newtons minus the 25.0 newtons is equal to what? 22.7 newtons. So why, I'm just gonna see if you guys know, why didn't we use the force of gravity there? Good, so we're moving in a horizontal direction right now. We're trying to figure out the forces moving across the horizontal so that we can eventually get down to what the velocity is across the flat surface. All right, so from here we now have our net force, and we can say F net is equal to mass times acceleration. So we have a mass that was given, it was mass is equal to 65.0 kilograms. So we're going to solve for acceleration so that we can eventually get down to time. So A is going to be equal to F net over M. A equals 22.7 newtons over the mass of 65.0 kilograms. Should get an acceleration of about 0.35 meters per second squared. Is that what everybody else got? Yeah, cool. Great. So we have this acceleration, and then we can use that to plug into kinematics and solve for what we're looking for, time, right? So I don't know where my formula sheet went. It's this one. Nope. It's this one. All right, that actually is hilarious. All right, so we're trying to find Our time, we have the values, acceleration, we have velocity. What formula do you guys think we should use? And we have the final velocity. The final velocity is supposed to be 10 meters per second. Initial velocity given was 2 meters per second. And then we just calculate the acceleration. So what do you guys want to use here to solve for time? Second one. Cool. This one. Great. So like I just said, we have V final. Remember the question said that he's trying to reach 10 meters per second. VI was given at 2.0 meters per second. Acceleration we just calculated is right here. And we're trying to find time. So it would be VF is equal to, just wrote it down and completely blanked. VI plus A times T, according to the formula sheet. So we just do 10.0 meters per second is equal to 2.0 meters per second plus the 0.35 meters per second squared times time. Okay? So we get 8.0 meters per second is equal to 0.35 meters per second squared times time. Divide that out. What'd you guys get as time? Should be like, I think it's 22.9 seconds. Yeah? All right. So it's about 23 seconds, but we'll just say 22.9. All right? Any questions about how we did any of those parts and pieces? We're good? Cool. Okay. So this can go. Okay, so this next one sounds very scary. It's not as bad as it seems. The setup is just kind of a pain. So a 650 Newton painter needs to climb 3 meters up on a ladder without the ladder slipping. The uniform ladder is 8 meters long and weighs 500 newtons. It rests with one end on the ground and the other against a smooth vertical wall. So the ladder rises at an angle of 60 degrees above the horizontal. And you need to find the friction force and the normal force that the floor is exerting on the ladder to keep it from like basically sliding off the wall, right? So if we were to draw a picture of this, we'd have the ground, we'd have whatever wall it's on, and we have this ladder, right? So more triangles. We have a painter, and we said that he was 3 meters up, so we're just going to draw him right there. This is our painter, so point P is going to be 3 meters from the bottom. Then we also have a total length of the ladder is going to be 8, so the center of the ladder is going to be point C. It's like the center of the ladder, right? And that will be at 4 meters, and that's where the center of mass is, right? So it's 500 newtons, so we're going to do C is equal to 4.0 meters, P is equal to 3.0 meters, and this is all from the bottom, so point A. So we'll say A to P and A to C, 4 meters and 3 meters. And then we also need the weight of the ladder, so we're going to say C for the center of the ladder, and that's going to be 500 newtons. And then we're going to have the weight of the painter, which is going to be 650 newtons. Okay? Let's see, what else did it give us? And then we also have a angle of 60 degrees above the horizontal. So to kind of conceptualize what this is trying to ask us, because it's asking for force, but how do we need to find those forces? What concept do you think we're going to need to use? We said it. I think you know it, though. Okay, it's torque, right? So the question is asking, like, what is the friction force and normal force that the floor must exert on the ladder to keep it from moving? So if we have at point B, this is going to be the force that's pushing on the ladder that's keeping it stationary. So it's going to be pushing like this around point A, correct? Same thing with point B. We have a force that's pushing up on the ladder, keeping it from sliding down, and it's going to be moving around point B like this. Does everybody see that now? So we have like rotation like this. Generally, we're talking about torque around some point, right? So, okay. So we are trying to find frictional force by the wall. And the normal force from the ground. And those two forces are keeping the ladder from falling. All right, so if we have something that's not moving, what does that say about the torque, the net torque of the system? It's 0. So I'm going to like draw my torque as a capital T. Generally it's tau, but I don't really draw the symbols. I like to just draw out the letters. So capital T is torque, lowercase t is time, just to keep it straight. All right, so torque here, net, is going to be equal to 0 Newton meters is the, whatchamacallit, units. All right, so the ladder isn't moving, and that's why. So ladder, not moving. So now we're going to go ahead and assume, or try to find the forces that are being applied by using torque. So the first case, we're going to assume that A is the point that is not moving. Or we are moving around, if you want to, moving around. So if we're moving around point A, which force are we solving for? What force is being applied by the wall? A frictional force, good. So we're trying to find force friction. All right, so this is what we're solving for, and we have to use torque to find it. So we said net torque is going to be equal to 0, but we're going to go ahead and set up to solve for net torque. So what are the components that are acting at point B? So if we're moving like this, what do we have acting there? Weight, by who? Good, so the weight by the painter and the center. So both the ladder itself is pushing down and the painter is pushing down. So what's pushing up to keep it from sliding? Frictional force by the wall. So we would do, what do you think should be the positive here of those three? So if we have torque being provided by the wall, torque being provided by friction that's not what I meant. Torque by the center of the ladder and torque by the painter. What needs to be positive and what needs to be negative? Again, what's pushing up, what's pushing down? Good, so the wall would be positive. What about the ladder? Negative, good. And what about the painter? Also negative, good, awesome. So we can write this as TW minus TC plus TP. And then if we remember, our net torque is still 0, so we can rewrite this again. And we'll get that torque by the wall, or torque friction, however you want to write it, is going to be equal to the torque provided by the ladder added to the torque provided by the painter. So what is the formula for torque? Do you guys remember? I'm not going to. You don't need to have that memorized. She'll give it to you. But so it should be this one right here, right? So force times radius times the angle. So we'll write that out. Is going to be force is provided. I'm blind. Oh no, that's what we're solving for. I'm done. Okay. Force by the wall is multiplied by the angle. So what is going to be the angle at by the wall? So we said that this is 60 degrees. That means that this is 30 degrees. We're trying to find the friction being created by the wall. How could we solve for that? This is one that's going to be a little bit weird. It's actually going to be cosine 30 instead of based off of this angle. You can also write it as sine 60. It'll be the same number, but in this case, I'm just going to use cosine the entire time, so I'm going to say cosine 30. Okay, and then times our radius. So the radius here would be the entire length of the ladder, which is the 8 meters. And that's going to be equal to the torque by the ladder, which is what? I have to write the formula. So if torque is equal to, oh my gosh, right there, FR, and then times either sine or cosine of theta. So either sine or cosine of theta, depending on which angle we're using. So what would we set? How would we set that up for the ladder? What's the force being exerted by the ladder? 500, right? So 500 newtons. This would be cosine 60 because if you guys remember the same idea with the whatchamacallit, the sliding block. We're going to have these little triangles right here. And so we're going to use cosine 60 times 3.0 meters. So this times this times this is going to represent the torque for the ladder. And we're going to add that to the torque provided by the painter, which is actually very similar. It's going to be 650 newtons times cosine 60 times 4 meters, I believe. Or no, sorry, this is supposed to be 4 meters. This is the ladder, my bad. 3.0 meters. You guys see that okay? Sorry, it's kind of long. And then you're just solving for this. So there's a lot of math going on there, but it's actually FW should be equal to about 285.1 newtons. Sorry, it's getting like crammed in this little tiny area. All right, is everybody okay with that? I'm gonna go ahead and start writing things down for part 2. I'll actually start like going through it in a second. So this is going to be pivot is at B, or the point that we're moving around is B. So we can remember that net torque is still 0. All right. Are you guys all done with part 1, or are you still working? Seeing some thumbs up. All right. So part 2, we're going to pretty much do the exact same thing, except for this time our point that we're moving around is at point B. So if we go back up to our picture, it's like saying this is the point that's not moving and we're moving around it, right? So if we were to set up this problem, it would still be very, very similar setup to the previous one, where we had our net torque. It's going to be equal to our torque done by what force? So we just solved for the frictional force from the wall. What are we solving for now? If this is the point that's staying put and this is the point that's moving, what force is acting here upwards? Normal force, right. So net torque is going to be equal to, is that going to be a positive or negative force? Positive, okay. So torque normal. What are our negative forces, or negative torques? I can't talk. Yeah, sorry, my bad. What are our negative torque values here? It's the same one as last time. So TC plus TP, right? Yeah. All right, so very similar setup again. We're going to remember that this can be plugged in. This 0 can be plugged in. We're going to rewrite the equation. So we'll have torque normal is equal to TC plus TP. and then we're going to just basically plug it all back in again. So we'll have force normal times cosine of 60. So the only one that differed here again was the cosine here on the wall, and that was because it was up, like on the wall, so that was the 30 degrees instead of the 60. So cosine 60 times the 8.0 meters is going to be equal to 650 newtons times cosine 60 times 5. Why do we use 5 meters? So let's look back at our picture again. So this is the point that's not moving. How far away is the painter from this point? 5 meters. So he was 3 meters from the bottom. The total length of the ladder is 8 meters. That means he's 5 from the top. Okay? So plus 500 newtons times, I'm going to kind of run out of space again, cosine of 60. And this will still be 4 meters because remember, our entire length of the ladder is 8. Our center is still going to be the center, it'll still be the 4 meters. So again, we're going to plug that one in, and you should get a normal force of 656.3 newtons. Okay? Any questions about that? Let's put that right on schedule. Okay, yeah. Yeah, so if we go back to this picture again, we have this triangle. This is our painter. This is the center of the ladder. Oh, you know what? This is supposed to be the torque by the painter. I think I got a little out of order, so that may help a little bit too. It doesn't really matter what order these two go to as long as they're added together. But basically, you were given in the problem that the distance from point A to point P is going to be 3 meters, and that the center of the ladder would still be 4 meters because it's 8 total, right? So when your point that you're moving around is point B, you have to go from point B to point P. So we could say point B to point P is equal to 5 meters because the total length of the ladder is 8. Any more questions? You had one, I think? Yeah. Okay, so that was just a way to rewrite it. So we know that net torque is going to be 0, right? Because we said we're not really moving, so we're static. So net torque will be 0, and we're going to have that set equal to the TW minus TC plus TP. And we're just going to move this. We're going to plug in the 0 and move it to the other side of the equation. So when you move it over, it'll actually be negative and negative. I know that's kind of a weird place to write that, but since it's negative on both sides of the equation, you can just divide out or multiply by -1, and it becomes positive. And so on this side, you'll plug in for the torque equation, which is the FD sine, theta or cosine theta, depending on your problem, I guess. But any other questions? Yeah. Yes, so you could say that this is the torque provided by the wall, or you could say that it's torque by the friction. The wall is providing the friction, basically. So it could be TW or T friction, whichever you prefer to write. I just put TW because it was a little bit shorter to write. Any other questions? No? All right. We'll go ahead and move on. I really hope that wasn't just picked up by the mic. I just drank water and it made a weird sound, so I was like, ugh. All right, so this next problem, you're going to exert a 200 Newton tangent, I can't say that word, a force that is at a tangent, to a grindstone of radius 0.26 meters and mass of 80 kilograms. The grindstone is a solid disc. So if we see something that's like, oh, it's a solid disc, or it's I don't even remember, like a hoop or something like that, what do you think that we're dealing with? Inertia, yeah, the moment of inertia. So we can go ahead and pull out our formula sheets in that case and circle, I think it was solid disk. Yeah, solid disk. So I'm going to go ahead and write that immediately because I know that I can use that formula. So moment of inertia is going to be equal to, well, I'm going to put I equal to 1/2 mr squared. Again, that's provided on this formula sheet. So, all right, so I'm going to continue reading the question. Sorry about that. All right, so it's a solid disk. What torque is being exerted? So drawing a picture might help some people. So then I'm also asking for angular acceleration, assuming no opposing friction, and the angular acceleration, if there is an opposing frictional force of 30 newtons, it's 2 centimeters from the axis. All right, so let's continue to go ahead and write out the given information. So the force applied equal to 200 newtons. We had a radius. It's given in meters, 0.26 meters. We had a mass equal to 80 kilograms. And then we have this next part, which is going to ask for a frictional force equal to 30 newtons and a radius that is 2 centimeters. So make sure you always use SI units. That's going to be 0.02 meters. Right? Sorry, I need to keep it to the one side. Move this? Nope, I should not move that. All right. So the first question is asking for torque. That's pretty easy. We can literally just look at the formula sheet, and it is a given formula. Torque is going to be equal to force times the radius. So torque is equal to force times radius. This is part 1. So torque is equal to the force was the applied force at 200 newtons times a radius of 0.26 meters. You should get a torque of, does anybody have it calculated? Yes, no? It should be about 52 newton meters. Right? And also if you wanted a picture, remember, this is your grindstone. That's not a circle, but we're going to pretend that's a circle. And we have a radius of 0.26 meters. And then we have an applied force of 200 newtons. And then the force of friction is going to be acting in the opposite direction, right? Should be a pretty easy little sketch. All right. So next question is a little bit more involved. Not a ton, but a little bit more involved. So the question is, what is the angular acceleration assuming no opposing friction? So we're solving for angular acceleration. We have torque, and we know the formula for a solid disk when we're trying to find moment of inertia. So if we look at our formula sheet real fast, should be, yeah, right here. So torque is equal to the moment of inertia times the angular acceleration. So it's another pretty easy one, a little bit more involved just because you have to know the moment of inertia equation. So this is going to be equal to torque over I. And again, the equation that she gave was torque is equal to I times angular acceleration. So I just rewrote it. This is going to be equal to the 52 newton meters that we just calculated over the 1/2 mr squared. So we have mass that was given, we have radius that was given, so this is just a plug and chug, 52 newton meters, 1/2 over I don't remember what the mass was, 80 kilograms, sorry. 80 kilograms times the radius, which was the 0.26 meters. Make sure you always square that radius if you're using the solid disk formula, because that is a very easy way for her to catch you guys and just be like, oh, this is super easy, it's this one, and then have it be like, oh no, I forgot to square the radius, which makes quite a bit of quite a bit of a difference in the number. So you should get that your angular acceleration is about 92.23 radians per second squared. Is everybody okay with that? Got similar number, same number, hopefully. All right. So then this last part, it's going to ask for the angular acceleration when there is an opposing frictional force, and that opposing frictional force is going to be 30 newtons, and it's 0.02 meters from the axis, so from the center of the circle. So we can't just jump in and start plugging in numbers, unfortunately. We have to actually find our torque again. So our net torque is going to be equal to what? Do you guys know? Zero? What are the components that we're dealing with here? Awesome. So yeah, that's exactly right. So she said torque, I keep wanting to say not torque. Okay, torque applied minus torque of friction, right? So going back to our picture here, we're applying a force this way. There's a frictional force acting in the opposite direction, so we're just going to subtract it when we go for our torque. All right, so we have to solve for this because we don't know what this is. We do know, or wait, I skipped something. We have to solve for the torque by friction. So if we go back to our formula sheet, again, we know that torque is going to be the force times the radius. So torque of friction is going to be equal to the force of friction, which is the 30 newtons, times our radius, which is very, very small. It's only 0.02 meters. So our friction is only, or the torque by the frictional force is only 0.6 newton meters. That's about it. So now we can take this number, plug it in here. We'll get T net is going to be equal to T applied, which was our 52 newton meters that we already calculated. We subtract our 0.6 newton meters. We don't have a huge change here. It's only, the 0.6, but it is still a change. So we should have a net torque of 51.4 newton meters, and then we can just plug that back into that same equation from earlier. Angular acceleration is going to be equal to torque net over the moment of inertia. So we get angular acceleration is equal to the 51.4 newton meters over the 1/2 80 kilograms times 0.26 meters squared. And you should get 19.01 radians per second squared. So not a huge change there, but you didn't exactly have a huge force that was acting on the grindstone, so it is still different, but not a huge change. All right, any questions about what we did there? All right. So this is the more recent stuff, so the stuff that you guys have not had an exam on yet. I did, I'm trying to think, 2 on like the buoyancy and then 1 on the simple harmonic motion. I did not include a question on sounds, so that's something you should review still. It's still on your exam. I just kind of ran out of space for including that in the review because we're already, 40 minutes out from the endpoint and we still have 3 problems to go. So I didn't think we were gonna have time to cover that. So make sure you go over sound stuff. It should still just be like the examples that we did in class on Wednesday and Friday. So there are only a few topics that you guys covered, but make sure you guys go over those. All right, so we have a rock with a mass of 540 grams in the air. It's found to have an apparent mass of 342 when submerged in water. So it's literally just like a pitcher of water, and you're sticking a rock in it, and when you do that, it apparently has a mass of 342 grams. So what mass of the water is displaced? What is the volume of the rock? What is the average density? And is this consistent with the value for granite? So we're going to write all this stuff down. So MI, that's going to be the, or wait, I think that's supposed to be, oh yeah, the mass initial is going to be, yeah, and mass initial is going to be 540 grams. We do normally use kilograms, but just for the sake of right now, we're going to leave it in grams. The mass in the fluid was the 342 grams. So the symbol for density that we use in physics is rho. It's like this funky looking P thing, so that's going to be my symbol for rho, just in case you're wondering. That's not like power or momentum or anything, that's density. So density of water is going to be 1,000 kilograms per meters cubed. If you guys remember from like your chemistry classes, the 1 gram per centimeters cubed, you're just converting it to SI units. And then the last question asks for the value of density for granite. So that value is going to be 2,650 kilograms meters cubed. Okay? Sorry, that's kilograms. My handwriting got a little weird there. All right, so we need to find the mass of the water displaced. So mass, we'll put, I guess, water. I don't know. Mass of the water displaced, the volume of the rock, so V rock, and then the density of the rock. Wow. All right, we're just going to rewrite that. Density of the rock. Okay. So what do you guys think that we need to do first? What? Volume of the water. So, sorry, I like yawn. When we're setting up for, one second, let me there's a formula. All right, so we're going to use the buoyant force here, okay? So we have to figure out the buoyant force in order to figure out, like you said, we're trying, sorry, I'm back up real fast. We need to find the mass of the water displaced, right? So in order to be able to find that, we need to use the buoyant force. All right, so I'm going to cross this out again. So F buoyancy is going to be equal to the displaced fluid, right? So, let's see real fast. I don't know if I like the way that I wrote this out. All right, so what is the buoyant force here? Do you guys know how we would write that? So it's actually, the buoyant force is going to be equal to the change in the mass times gravity. Okay, so we have gravity is acting as the downward force, and again, we're talking about this pitcher that we're putting the rock into, so your downward force is this gravity, and then we have a change in mass from the initial to the final, and then this is going to be equal to the mass of the water times gravity. That's right here that I use. It's fine. All right, so we know that this is going to be the change in mass. So we wrote up here, we had the MF minus the MI. No, it should be MI, sorry. No, wait, what did I do? I'm sorry, I'm going off of what I wrote in my notebook, but I didn't actually write out the steps. I just was here's the math. All right, so it should be mf minus mi. I think that, yeah, all right. Is equal to the mass of the water. So this is going to be equal to, because we canceled out the gravity here because it's the same on both sides. I don't know. All right, 540 minus 342 grams is equal to 198 grams. I think that's where I screwed up. Yeah, sorry. I like made a math error somewhere.
You did mass initial minus.
Yeah,
She has in her notes that you put in absolute value, so
yeah. That's where it was. Thank you. This should be absolute value. That was like looking at it and I was like, there's definitely something wrong here. I started to write the absolute value and then I changed it to parentheses at the last minute. That's the problem. So it should be, thank you, 342 minus the 540, and this will still come out to the 198. It'll be negative, but it is absolute value when you're doing the change there. So it should be positive 198 grams. Yeah, so that's correct. All right, so would be the 198 grams. We have to convert this now to kilograms. We didn't earlier, but it was just because, I don't know, it doesn't really matter. It still comes out to kilograms. So that would be the mass of the water. Sorry, this is an interesting work through, but yes, this should be absolute value when you do the delta M. This is correct. So this is mass of water. Sorry, that was not the greatest thing ever because I did not write that down well. All right, part B, we're trying to find the volume of the rock. So we do velocity, or not velocity, I keep wanting to say velocity. Volume of the rock should be equal to the volume of the water that we displaced. So basically, you're sticking this rock into this pitcher of water, and you're going to have some displacement, and whatever the displacement is will be the same as the volume of the rock. So we know that our volume is going to be involved in the density equation, and we have mass now, so we're going to use that equation because we have our density and we have our oh my gosh, our mass now, so we can use the density equation. So this is going to be m over v, and it's going to be equal to the mass of the water over the density of water. So volume is equal to mass of water, which we calculated to be 0.198 kilograms over the 1,000 kilograms per meters cubed. So this is going to be a very small number. It's about 1.98 times 10 to the negative fourth meters cubed. Did everybody see where that came from? Yeah, okay. Yes, so the volume of the rock should be the same as the volume of the water displaced. So we went ahead and found the volume of the water displaced, and that gave us the volume of the rock. All right. All right, so part C is then to find the rock's density. So we're going to use, again, the density equation. Remember, our little p stands for density. So density will be equal to mass of the rock over the volume of the rock. And so we just found the volume of the rock up here. Sorry. So we can just do p of the rock is equal to the mass of the rock, which was our 540 grams is what we're going to use here because of, we're using the 540 grams because that is the, the mass in the air. So we do need to convert this to kilograms though because our SI unit should be in kilogram. So that should be 0.540 kilogram all over the, that we just calculated, the, volume. 1.98 times 10 to the negative fourth meters cubed. That's going to be equal to, I have to double check. Cool. That should be equal to 27.3-ish, give or take. She generally does 4 sig figs, so we'll just leave it at 2,727 kilograms per meters cubed. And so we said up here that we had a density of about 2,650. That's according to Google. So like, it's close enough that we can assume that this is granite. So, oh, sorry. So this is close enough. Oh, dang it, I can't spell. This is granite. All right, we're just gonna write granite. We're good. We're close enough to that value that was given. So if you guys have a problem that involves buoyancy, she'll give you most of those values. I do imagine that she would probably expect you guys to know the density for water, since it's just 1,000, and it's pretty easy to convert. If you remember the one from like chemistry classes or whatever, you're just converting it to the correct SI units. Cool. All right. I don't like that problem. So number 7.
What is the density again?
Density of water is the 1,000 kilograms meters cubed. So I think in chemistry classes they do grams centimeters cubed. That looks familiar. Yeah. Yeah.
I've seen a couple exercises where the object is not completely submerged. How do you do it if it's not completely?
So when you have, I'm trying to think, remember. So when you aren't completely submerged.
When you're floating, if the object is
Mm-hmm.
floating.
What do you guys think? Does anybody have any advice?
Said like 3/4 of the
Object is submerged. I'm trying to remember.
fraction of.
Yeah. Just per area. Heat is equal to pH fraction submerged. So it's this here. She gives this to you. Fraction submerged is going to be volume of the substance over the volume of the object is equal to the volume of the fluid over the volume of the object. So if you have you would have to find still the volume for both, and then since it's a fraction, you would divide the fluid by the object. If that makes sense. Does that make sense? Kind of, okay. Yeah, so she gives, I like compare my formula sheet to hers generally to make sure that, like, I don't want to include too many of the formulas if she, like, doesn't have one. So this is from her formula sheet. So this is given on your guys' exam according to what's underneath your exam materials. There is like one formula that I did add that I know that she didn't have. We're going to get to it, I think, in this next problem, and I will like point it out and be like, remember this, basically. So she may end up adding it to your guys' formula sheet, but as of right now, it wasn't on there, so I don't know if she's planning on it or not. So suppose you attach the object with mass m to a vertical spring originally at rest and let it bounce up and down. You release the object from rest at the spring's original rest length. Show that the spring exerts an upward force of 2 mg. So this is actually mass gravity. That was why I picked this, because it was kind of a weird problem. So 2 mass gravity on the object at its lowest point. The spring has a force constant of 10 newton meters, 10 newtons per meter, and a 0.25 kilogram mass object in motion as described. Find the amplitude of the oscillations and then find the maximum velocities. So again, we're going to go ahead and write down our knowns just because it makes life a little bit easier. So we have the spring force constant. So this is our K value, and that's going to be equal to 10.0 newton meters, or newtons per meter. And then we have a mass that is added, and it's 0.25 kilograms. We have gravity, and this time we are going to go ahead and take it at 10 meters per second squared. And I think Yeah, this is a constant, so just remember the K constant, right? Okay, so we need to find the upward force when the spring is going to stretch to the lowest point, the amplitude of the oscillations, and the Vmax. So we can write that as well. Upward force when stretched. Amplitude. And then the Vmax. Okay, so get rid of that, get rid of that, get rid of that. We're going to draw a picture. So if the spring is at rest, it's just going to be doing its thing. It's not very exciting. Then we have added a weight, which is going to stretch out the spring. It's going to be way down here. And then if we were to pull that way down and then let it go, it's going to come shooting up, scrunch back up again, and then start bouncing back down again. So it'll have some point of very scrunched up spring. Looks like that, basically, right? So remember, this is simple harmonic motion. So we should have an equal distance between this and like the resting point, basically. This is not drawn to scale, but this should be about the same, those two values right there, okay? All right, so the first question asks to find the upward force when this is like stretched, and then in order to do that, we have two net forces. We have the net force at the top, and we have the net force at the bottom. So we're going to take that as a negative, right? So basically you stretch it out, you let go, and it's going to scrunch up. So one of these values needs to be positive, one of them needs to be negative. All right, so basically what this wants us to prove is that when our spring is completely stretched out, we have a upward force of 2.00 m times g. This is not milligrams, this is mass times gravity, okay? All right, so in order to do that, we're going to have to do some rearranging. We have that the F net at the top is going to be equal to what? What forces are acting at the bottom? Gravity, good. So we're going to have F net top is equal to a force of gravity. And then we have another force that's acting. And actually, I forgot like a negative sign. So what other force is acting? Speed force? Spring force. Okay, I was like, speed force. Okay, sorry, I can't hear. So the force from the spring, right? So it's stretched out. It doesn't want to be stretched out once return to normal. It's got a force acting. So what is our value for Fg? Force of gravity. What? Where'd you get that from? Okay, so we're going to talk in like variables, I guess. Sorry, I should have explained that better. We're talking in variables right now because remember we have to prove that this is exerting a force of 2 mass times gravity. So what is an Fg? Mg, okay. All right, so negative mg plus Fs, right? And then we have this other force. So when we're at the, actually wait. Did I do that right? I take that back. 1 second. Okay. Sorry, I was like getting ahead of myself. This is the top. We're solving for the top first. So this is not negative. This is positive. My bad. All right. I don't know what I was doing there. So we would have the top should be positive. We said that it was positive. I was solving for the bottom instead, and that was not correct. Okay, so I'm trying to think. So looking at this picture again, when it has contracted back up into this little like squished version of itself, I guess, what forces are acting on it? Do we still have the gravitational force acting on it? Yes, it wants to come back down again. It wants to extend like your accordion, basically. So we would still have the force of gravity and the force of the spring. What do you guys think? I'm trying to think.
At the top, wouldn't it be negative, and then at the bottom it'd be positive, since it's going back up?
For what?
For the force of the spring.
You think this would be negative? Okay. So I'm going to like rewrite this since I started getting off on a tangent and moving ahead of where I was actually at. So we're going to rewrite this real fast. My bad, my mistake. Okay, so F net is going to be the top. We're going to find this first. So we have the two forces that we have acting there, and those are going to be the force of gravity, we decided, and the force of the spring. We know that the force of gravity is going to be mg, and actually, wait. I take this back. Force of the spring. The force of the spring is actually going to be 0, so I keep getting ahead of myself because I'm like trying to go faster, and that's a mistake. Okay, so the force of the spring is actually 0 because we're not here, we're here. So we still have a mass here. When we attach the mass to the spring, it's going to hit that point here. And we'll still have the force of gravity acting on it because we have this mass that's trying to pull it down, and then we would have the force of the spring is 0 because it's not stretching, it's not contracting, it's kind of at rest, basically. So then, I'm sorry, I got way ahead of myself. It's like, let's do the bottom first, and I was like, no, that's wrong. Okay, so F net at the top is going to be the mg plus 0. So then, and actually, we would normally, to find the force of the spring, we would multiply it by the k constant, but again, this is the 0, so it doesn't matter here. And then we have, this will still end up being mg, right? So then we need to do F bottom, sorry, again, I got way ahead of myself. And this is going to be the opposite of what we were just talking about. So not at the bottom when it's completely stretched out. And that is going to be our what? Are we still having the force of gravity and the force of the spring? Yes, good. So force of gravity plus force of spring. These will both be negative because it's in the opposite direction. So if we plug it back in here, we'll get the mg is equal to negative mg minus the force of the spring. And then if you rewrite this, you'll end up getting that the force of the spring is equal to 200 mg. I apologize for that being as painful as it was. I skipped around instead of moving in one direction. Okay, so that should be that you have proven that it is in fact the 2 times the mass and gravity. Sorry. When you've been doing physics for this long, it's like sometimes you jump around a little bit. All right, so the next part is going to be to find the spring has a force constant of the 10 newtons per meter, and a 0.25 kilogram mass object is set in motion as described, and you need to find the amplitude. All right, so we just found out that the Fs is going to be equal to the 2 mg, right? So the 2 mass times gravity. And from our formula sheet, this is the second page. Where is it? Simple harmonic movement. Yeah, sure. Yeah. Let me double check one thing, just because like I kind of, again, I'm like screwed myself up a little bit. All right. It's this formula. let me reread the goal. Show that the spring exerts an upward force of 2 mgs on the object at its lowest point. At its lowest point. I think that it's based off of FG would be able to have x squared. Sorry, I'm trying to remember. That's it. Okay. Displacement would be 0. Would be the force that exerted by the spring. Force would be 0. So if I remember correctly, it is actually the top. Sorry, I'm like bouncing around and the physics is getting in my head. It actually, I think, is the top, and this 0 is, it normally is the force, all right. Force of the spring is going to be equal to K times X, where X is the displacement. And since you have some value from the stretch and some value from the top, it'll be the same. And so since you have, this is your initial position, and then you're going down, and then you're going back up, your displacement is what? From your original starting position? 0. Sorry, I don't like this problem. I don't know, I like jumped way down here and started writing, and then I was like, I just like jumped around, and then I messed myself up. I was like, oh my gosh, I screwed up. So anyway, so yes, I apologize for that. It is actually the top. It's because the displacement is 0. My brain, I apologize. Anyway, so Fs is equal to 2mg, and this is going to be equal to, again, so the force of the spring here is going to be K times displacement. In this case, we have 2 amplitudes. So we're trying to solve for the amplitude, I believe. Yeah, so the amplitude of the oscillation. So we have 2 amplitudes that we have to consider here. So we're going down, we're going back up. So we're going to plug in 2 amplitudes for x. So this is actually a pretty easy solution. We're just going to do that A is what we're solving for. So you rewrite this equation here, and you'll get A is equal to 2mg over 2k, and this equation here, sorry, so you're basically doing 2mg is equal to k times 2a. We're gonna go like that, and then you rewrite it to get this, and then you plug in. So A is equal to 0.25 kilograms times the 10 meters per second squared, all over the 10 newtons per meter. So we went ahead and canceled out the 2's because there were 1 on both sides, and you get that the amplitude is 0.25 meters. I still hate this problem. All right. Next part is part C. I'm like running out of space again. So part C is to find the maximum velocity. So in this problem, we have to use basically, we're using energy to be able to find it. So we can do energy in springs, basically. So we know that energy is going to be conserved because this is a nice system here. So in order to basically find this, we have formulas somewhere. Which formula sheet is it on? Sorry, trying to make sure that I have the right formula sheet. Yeah, so this is on your guys' formula sheet. It was not on the formula sheet that Dr. Rahman gave you, so I just want you guys to be aware of this. The PE equals 1/2 kx squared. So I'm gonna write that here. PE equals, I just forgot it already, oh my gosh. 1/2 kx squared. All right, so that is the potential energy of a spring. So in order to find, the question is asking for the maximum velocity. So we have to solve to find the, the velocity. So we're going to use potential energy and kinetic energy. So kinetic energy will still be 1/2 mv squared. So we can use this formula. We have EI, so it's going to be the energy is going to be equal to the potential energy of the spring, which is this formula here. Energy. Yeah, oh, sorry, I can't see. It's like weird seeing it over there. All right, so the potential energy of the spring plus the potential energy of basically provided by gravity. So again, kind of using those same concepts of the spring and the gravity. And then we do have kinetic energy. Or do we? Do you guys know? All right, so sorry, I think I didn't mention that this is going to be our initial energy. So EI is initial energy. So if we have a spring, do we have kinetic energy when it's just at rest? No, so this would actually be 0. All right, so we just have the potential energy by the spring and the potential energy by gravity. We have this formula here that's the 1/2 kx squared. We can use A as the displacement because it's the amplitude, right? You guys know where that comes from. K amplitude squared, and then potential energy by gravity. Remember from the energy chapter that it's mgh is the formula for potential energy normally. The height here would be the amplitude still. So it would be plus mga, and then this would be equal to, and then plus 0 because the kinetic energy is still 0. And then we have, so this is our formula for the initial energy. In order to find the total, we're at the end, remember we do energy is conserved, so EI will be equal to EF. So EF we have to solve for is going to be equal to potential energy by the spring plus potential energy by gravity plus kinetic energy. Do we have potential energy in the spring when it is moving? If it's like moving, is it, are you sure? No, okay. Okay, so if you think about normal potential energy, if you're, I don't know, rolling down a flat surface or something like that, you don't have potential energy. So it's similar here. You have 0 potential energy for spring, and the gravitational and the kinetic energy would still be the 1/2 mv squared. So like we said, the initial energy will be equal to the final energy, and we know that from the conservation of mechanical. Same here, conservation of energy will occur. So we can plug in here. So we'll have the 1/2 Ka squared plus Mga is equal to 1/2 Mv squared. And then we're going to solve for velocity. I'm going to go ahead and I'm not going to be like, oh, and you add this here and divide here. I'm just going to write out what you should get when you move things around. You should get the velocity is equal to the k constant over m times amplitude squared plus 2ga. And then you're just going to plug in numbers. So velocity will be equal to 10 over 0.25 times 0.25 squared plus 2 times 10. This is gravity as 10 instead of the 9.8, 0.25 at the amplitude. So you should get that your final velocity is 2.74 meters per second. Sorry that problem was kind of a pain. All right, I only have about 5 minutes left, so I don't know that I'm going to get all the way through question 8. Would you guys prefer, what do you guys want me to do? Do you want me to start it and then leave it, or what do you want me to do? I don't know, it's up to you guys. Set it up, sure. All right, so question 8. So this is the twin size mattress thing. I like the question because it reminded me of the Parent Trap. So you have a twin-size air mattress used for camping. It has dimensions of 100 centimeters by 200 centimeters by 15 centimeters. And you want to know, you have the weight of the mattress, it's 2 kilograms, and you just basically want to know how heavy a person could be if it's placed in fresh water. So how heavy can that person be sitting on top without it sinking? So the first thing to do would be to go ahead and find the volume. So we have that. We're going to do mass is 2 kilograms. Dimensions are 100 by 200 by 15. So this all needs to be converted back into meters to get the right SI unit. So it would be 1 meter times 2 meters times 0.15 meters should be 0.3 meters cubed. So that is your volume. This is volume of mattress. Okay. So we know that density of water is the 1,000 kilograms per meters cubed, and we already wrote the mass, so you need to find the mass of the person. So we know that the force of buoyancy is going to be equal to the fluid displaced, so the weight of the fluid displaced. I think earlier I just put W, fluid displaced, but it's supposed to be the weight of the fluid displaced, and I apologize for not explaining that better. And then we know that the force here should still be mg, because remember it should be mass times acceleration, in this case gravity. And then we know that the mass total will be equal to mass time of the person, not times the person, of the person plus the mass of the mattress. We know that the force of the buoyancy is equal to the weight of the person here. So this will be equal to the mass total times gravity. So if we know that force buoyancy is equal to mass total times gravity, which is also equal to the weight of the fluid displaced, as we already covered, this is going to be equal to the mass of the water times gravity. So that means that if we have this is equal to this, this is equal to this, and this is equal to this, that will have that the mass total times gravity is going to be equal to the mass of water times gravity, and we can get rid of gravity on both sides. So we'll have the mass total is equal to the mass of the water, which means we'll also have the volume of the mattress in water is going to be equal to the volume of the water that's displaced. So if we know the density of water, and we can, I'm trying to think. We know the density of water, we know the volume of the mattress. So we can do volume of water equals the mass of water over the volume of water displaced. And we can use that to, I'm trying to think. We already covered that mass total. Yeah. Is equal to mass water, which is equal to the density of water times the volume of water displaced, right? So if we know that, then we can go ahead and find that the mass total is equal to the 1,000 kilograms per meter cubed times 0.3 meters cubed, and that will give us 300 kilograms. So then we know that the mass of the person that you can have is going to be equal to the mass total subtracted by the mass of the mattress. Mass mattress is equal to 2 kilograms. Mass total is 300, so you just do 300 kilograms minus 2 kilograms. The max weight that you can have for a person on the mattress would be 298 kilograms, which is actually a surprising lots of weight. So you could have a potentially pretty large person hanging out on a mattress in the middle of a lake, which is pretty cool. Anyway, that's the end. I apologize that those last few questions were kind of rushed and all over the place. that's all I have. If you guys have any questions or if you want any advice regarding your exam tomorrow, you can come and ask it. I will ask you to fill out one of the surveys on one of the front tables over there. I think it's like the front one right there. And just like give it to me. You can be honest. I'm not going to be like hurt if you're like, this was the worst or anything. Like, please be honest. I take it as good feedback. But I don't know. Please make sure you fill it out. I lost the thing. It asks you to bubble in a number at the top. That number is 50. So 50, it's that one. If you have any questions, though, please ask. And if you need to take pictures of anything, you can also do that.